Hi, this is Dan Bullard, retired electronics engineer out on the river again. We're getting there. We're past solstice and now we're just waiting for the sun to come back. I want to talk about op amps again and another government fuck up. Because remember, I worked for both Ministry of Aerospace, which is China, and they're pretty fucked up, and the U.S. military. And all you have to do is watch the Pentagon Wars, and what a disaster. Kelsey Grammer is great in that one. I won't tell you which government did it because the FBI will come after me if it turns out it's them, if they're willing to admit it's them, but they're not going to. Of course, you never know. Roger Stone probably said the same thing. Anyway, in op-amp specs, there's usually a spec for CMRR, which is common mode rejection ratio. CMRR. And what that says is, if I have a, let's say I have a transmission line, twisted pair, and it's going to go, the smart thing to do is go straight to an op amp, and ta-da, it amplifies the differences between the two inputs, the plus and minus. That's a differential amplifier. And if you do it right, if you set up right, then the differential amplifier means that it'll cancel out anything that's picked up on the differential pair along the way. So anything that's common between the two inputs is rejected. And that's common mode rejection ratio. So for this military contractor, I took a look at a test that they did. They were injecting a 10 kilohertz sine wave into the device. And so they injected it into just the positive input with the op-amp connected in negative feedback configuration. And they would get a baseline on that. And then they would connect a relay to connect both positive and negative input to the same 10 kilohertz signal, and then look at the output again. Now you got to remember, CMRR is usually like 60, 70, 80, 90 dB, maybe 100 dB, which means that you're not going to get much. And one of the big problems they made right away was they did, obviously, you have to do range changes, because then the output's going to be a 10 kilohertz sine wave, very large. But when you do the common mode test, wow, that was a big one. When you do the common mode test, common mode rejection ratio, wow, I haven't felt anything yet. So when you do the common mode rejection ratio test, those two inputs are now connected, and so the output is very small, very, very small. And if you're putting a 0 dB signal in, you're going to get out something like 60, minus 80, minus 90, minus 100 dB, which is pretty tough. Now, that means you got to be careful about things. So you'll love this. You know, I talk about FFTs all the time, but they're a godsend. They really are a godsend. So what these guys were doing was they were capturing the signal, and the source waveform, the 10 kilohertz waveform, happened to have, it was generated by a clock. It was also picked up on the capture side, and the capture side picked up the same clock, so it could capture the 10 kilohertz. So what they decided to do was, when they measured it with the common mode test, it was really tiny. The signal was very tiny. So what they did was, you can't change the ranges. So what they had to do was, they had to try to eliminate the noise. Now, they captured a lot of samples and went looking for the signal using, I even hate to say it, using 0.7 times the peak, so to get the RMS. So 0.707 times the peak gives you the RMS. And it was pretty bad. It was very noisy, obviously, because it's a very low level signal. So they would amplify the shit out of it by capturing it multiple times. That is, they started with, I think, 1,000 samples. And it wasn't enough. So they took more. Now, they were going to get one sine wave with 1,000 samples. So then what they did was they went 2,000 samples. That's 2 sine waves. 2 sine waves. And that averages out the signal and the noise. So the signal kind of comes, it's reinforced, and the noise is averaged out. And as you may know, it reduces the noise by 3 dB, for each doubling the number of samples. Well, 2,000 samples wasn't enough. So then they went to 4,000, and then 8,000, and 10,000, and 20,000, and 30,000. They eventually stopped when they got decent numbers at 4 million samples. 4 million samples. Now that took 10 seconds to do that test. 4 million samples. And still, the noise was overwhelming, and so they had to reject the positive and negative peaks. I think the first or second positive or negative peaks they captured, and then they went with whatever the peak they could find and worked out 0.707 times the peak. That's the RMS, and they said, oh, that's good. And the CPK, which is, it's a statistical thing that you use to make sure that your test is valid and reasonable. The CPK was kind of iffy, but they went with it. So they took 4 million samples and got kind of okay CPKs. Now I took a look at this because I'm an op-amp expert and I'm an expert at mixed signal, and I realized what they were doing was incredibly stupid. So they weren't using an FFT. What the hell's wrong with them? What the hell is wrong with them? They were just rejecting whatever they thought was noise and figuring, okay, this peak times 0.707, that's the RMS. So I went in and I rewrote the code so that I sampled 8192 samples. 8192, 8,192. That is 500 times fewer samples than they took. Now, 8192. Why did I take 8192? Because it's a power 2. Power 2, I can now do an FFT. So I did an FFT, nailed it. Got it right away. And I got better CPKs than they ever got. And I limited 10 seconds of test time. 10 seconds. Now in a production environment, you'd get a medal for that, you know. But this was a military thing, so they could care less, right? It doesn't matter if it takes 10 years. They don't care. So I did the test. I showed them the CPKs. I showed them the numbers. I showed them the technique. They said, no, that's okay. It works just fine. Yeah, sure, it works kind of okay, but it's not even really legitimate, right? When the advantage of doing an FFT, in case you didn't know this, is that the noise is spread out among all the bins, where originally they were taking the average and then looking for the RMS. There's no noise rejection there, no noise rejection at all. But when I do the FFT, then the noise is rejected a lot. So now the signal is in one bin, and I forget what bin that was, but here it is. Here's the signal, and you can see that their signal looks like shit. My signal, on the other hand, it's beautiful. Now you may wonder why it's beautiful. What I did was, I took those 8192 samples, I did the FFT on it, then I took the amplitude in whatever bin that was, bin 9 or whatever that was, and I got rid of everything else. So there was nothing else in the spectrum except the 10 kilohertz. So I got rid of all the noise, and I can do that. I can easily do that, and it's perfectly valid. The only thing I care about in the CMRR test is 10 kilohertz. So I just ignore everything that's not 10 kilohertz, and I'm good to go. So anyway, that's it for now. From the river is Dan Bullard.